So today, I'm going to talk to you about our vision for continuous compliance and how we've implemented it. And my name is Martin Kellogg from the University of Washington, and this is joint work with my colleagues Martin, Serdar, and Mike from AWS. All right, so first, what is compliance? Well, suppose that you're a software developer or a company that develops software, and you want to sell some software to a customer. Typically, this would work by you sending them the software and them sending you some money in some very high-level form. But for certain customers, like large organizations, like governments or banks, just sending them the software isn't enough. They are going to need some assurance that the software is secure. And in industry, this typically works by doing what's called a compliance certification process. So for instance, if you're handling credit card data, you might need to be certified by the PCI DSS. And there are a variety of these sort of certifications. These certifications tell the customer that you're following the bare minimum of security best practices. Right? You're not going to do something egregious like leak all of the credit card data across the whole internet. And the way that this works is that you, as the vendor, are going to hire an external auditor. And the auditor is going to look at your code using an audit process and decide whether they think that your code is up to the standards that the compliance certification process requires. And if it is, then they're going to give you a certificate that you can then show to your customers. And for a lot of these sorts of important kinds of business, you simply can't do any of the work that you need to unless you have such a certification. So today, what I want to focus on is this process of actually getting certified. When you're talking to the auditor as the developer, how does it work? So let's look at what a traditional audit workflow looks like. We're going to look at the three stages. The first stage, development, is when you're actually writing the software. And as a developer, what you have to do is keep compliance in mind when you're doing code reviews, when you're writing code, and so on. Then in preparation for the audit, either the developers or an internal compliance team is going to gather evidence that the rules for the compliance process are being followed. These rules are called controls. And the controls are typically quite simple. Right? The ones involving source code are usually things like use strong encryption, right? Or don't use hard-coded passwords. Right? And then finally, in the review stage, an auditor is going to come on site and randomly sample from the evidence that was gathered during the preparation stage and manually check that the rules are followed. So for example, one of the pieces of evidence might be a screenshot of where customer data is encrypted. And the auditor will look at it and say, well, I can see that you're using an encryption algorithm that I know is particularly strong. And so that's fine. There are some problems with this approach, though. I want to show you four. The first is cost. This process is incredibly labor intensive. It requires humans to be involved at every stage. And they often have to be paid quite well. Next is the problem of human judgment. This process, again, is extremely labor intensive and entirely relies on the humans to get it right. And as we all know, humans make mistakes sometimes. None of us are robots. The third problem is that this process is heavily reliant on statistical sampling, which means that even if you gathered all the right evidence, it might still not be shown to the auditor, and they might miss something, which would be both bad for you and bad for your customers. Lastly, this process is prone to regression. Developers have a lot on their minds and often aren't thinking about compliance when it's not audit time. And so code can get out of compliance relatively easily. So that brings us to our proposal, our vision for continuous compliance. The way that continuous compliance works is that each of these controls, rather than being enforced by a manual check, is going to be enforced by an automated verification tool. We're going to run that verification tool in the continuous integration system for the developers themselves, and then report failures directly to the developers so that they can fix them as soon as they happen, preventing the regression problem. And in a continuous compliance workflow, the audit system is going to look a little different. In the development stage, the developers are going to write a few specifications, and in our experience, not many. I'll show you some more about that in a bit. And then the verifier will run during continuous integration and alert them to any problems. At the preparation stage, there'll be no work to do. The developers won't need to do anything else. And at the review stage, the auditor can just check the output of the verifier. And this only works because the verifier is sound. It's a verification tool. So if the verifier outputs that there are no problems, then the auditor can trust that, in fact, there aren't. Auditors are unwilling to accept something that isn't to this standard. How does this handle the 4 problems I noted with the manual approach earlier? Well, it's much better in each. On cost, because it relies heavily on automation, it's much cheaper. And developers seem to have spent less time in our experiments and case studies writing the specifications than they did for each audit, preparing evidence before. So that handles cost. For judgment, it's fully automated, so there's almost no judgment involved. For sampling, the verifier runs on the whole system, so that's great. And for regressions, because it's running in CI, developers can fix problems much faster. So these are no longer issues. So what did we contribute? So first, as I've already showed you, the idea of continuous compliance, and that verification is a good fit for compliance generally. Second, we have an engineering contribution. We've built 5 verification tools that match directly to common compliance controls. And then we have an experimental contribution. We've run open source experiments using these 5 verification tools and comparisons with other off-the-shelf tools that you might think would be a good fit for handling these sorts of problems because they're designed to catch them, but aren't sufficient for the needs of continuous compliance. And finally, an experiential contribution. So we've worked with our colleagues at AWS to integrate verifiers into the compliance process that they use. So 5 compliance controls. So the controls are the 5 listed on the screen, that HTTPS is used rather than HTTP, that cryptographic keys are of sufficient length, that cryptographic algorithms that are selected are off of the allowed list that the compliance regime specifies, that cloud data stores such as Amazon's S3 buckets are initialized in a way that is safe, that is, they're not going to be world readable and that they're going to store metadata and so on. And that hard-coded credentials are not used. And these are compliance controls that are common to many regimes. And to handle these, we used mostly off-the-shelf verification techniques, right? There's no algorithmic novelty here. But just to give you an idea of how this works, the techniques. So for the first control, we used just a constant propagation algorithm. For the second, we added to the constant propagation algorithm an enum analysis that does constant propagation for enum values. For the third, we added a regex matching capability to handle the allow lists for the cryptographic algorithms. For the fourth, we used a technique called accumulation analysis. That's a form of type state analysis that doesn't require whole program inference. And for the fifth, we used a data flow analysis similar to a taint tracking system. And then all of these are known. And then for our analysis strategy, our implementation strategy, we used type systems. And the reason for this was that we wanted to run these tools on a large number of Java programs, and we needed to be able to interact with our developers, who are, at least these services were all written in Java. So they're already familiar with type systems, which is a big advantage. And then type systems have a couple of other nice properties that make them a good fit for this system. They're predictable, scalable, and sound. But in theory, there's no reason you couldn't use any kind of sound verification technology for continuous compliance. And then we evaluated these systems in 4 ways. And this is where the real meat of this work is. So I'm going to spend a lot of time. But these 4, first, we ran all the verifiers on 492 open source projects from GitHub. And second, we compared the verifiers to existing tools for detecting security problems and showed that though those existing tools are extremely precise, they're insufficiently sound for the needs of the compliance auditors. Third, we ran a case study of using one of the verifiers as part of a real compliance process at AWS. And in the end, AWS's external auditors accepted the output of the verification tool. And finally, we ran another case study at AWS where we included our verifiers as part of security scanning infrastructure and showed that they work extremely well at AWS's scale. So first, open source projects. So we pulled these projects from GitHub. They were selected randomly from among those projects that use the APIs that are relevant for compliance. And they totaled a little less than 6 million lines of code, non-comment, non-blank. And then we used a type inference engine and a build scanning process to totally automate this. So we didn't write any specifications in these programs, and we threw away those which we couldn't use. And we triaged the results into 4 categories based on 2 axes: whether they contained real compliance violations, that is, whether a compliance audit would have rejected them if they had been used to handle customer data, and whether our tools issued false warnings on them. That is, whether our tools issued warnings that did not correspond to true compliance violations. And then we just bucketed each project. If the project's warnings were all true positives, that's the only way for it to end up in the true positive category. The results look like this, where each of these squares corresponds to the area of each square corresponds to the number of projects. And there are two sort of takeaways that I want you to take from this. And the first is that if you're a compliance officer, about half of the open source projects we examined have at least one true compliance violation. So if you're using open source projects as part of your workflow for customer data, you should subject them to the same level of audit that you subject your own code. Second, the top half here, the half without false warnings, is about 2/3 of the projects. So our false positive, or our tools issue false positives on less than 1/3. All right, next. The next thing we did was compare our verifiers to existing tools. And the way that we did that was we used a previously published benchmark called Crypto API Bench that was used for evaluating security bug finding tools. And we compared on categories that are overlap with compliance. And we compared our tools to 4 other tools that had previously been evaluated on this benchmark. Spot bugs, augmented with some additional security patterns as a heuristic-based bug finding tool. Coverity, which is a closed source commercial bug finding tool based on symbolic execution. CogniCrypt SAST, a recent tool based on the soot data flow framework that's, again, for finding security problems. And CryptoGuard, which is also based on the soot data flow framework, but augmented with slicing. And it's worth noting that Crypto API Bench was designed to evaluate CryptoGuard. So we evaluated on sort of 2 axes, precision and recall, sort of in the standard way, where precision means a perfect precision score means no false positives, and a perfect recall score means no false negatives. On precision, the best tools are Coverity and CryptoGuard, are both perfect. That is, that they never issued a warning that didn't correspond to a real problem. But our tools were nearly as good. They issued a few false positives, but many fewer than Spotbugs or Crystal. On the recall side, though, things were a little different. Only our tool achieved a perfect score, and the other scores range from very poor to fairly high with CryptoGuard. But I want to point out here that this shows that off-the-shelf bug finding tools are not sufficient for the needs of a compliance auditor, because they do miss alarms. And compliance auditors won't accept tools that have false negatives because then they would feel that they'd still need to examine the code by hand themselves. Next, we ran a case study of one of our verifiers in a real compliance workflow at AWS. So for this, we used the key length verifier, that is, that checks that the length of encryption keys is sufficiently long. And we added this verifier into the CI process for 7 core AWS services that you've likely heard of. And this replaced the existing manual compliance workflow, and AWS's third-party auditors accepted the results of our verifiers, which were that all the services are in fact compliant, as one might hope. And we have some quotes here from those involved in the process who will let you know what they feel. So first, the external auditors, that is the company AWS hired to audit them, tell us that it eliminates the need for a lot of the trust that they previously had to have in AWS's engineering teams. And they really were very happy about this. And let me show you one example of why. So this is some code that our tool issued an alarm on. You might note here that there are 2 paths through this code, one of which uses a key length of 128 bits, the other uses a key length of 256. And the auditors were looking for only using 256-bit keys. So they initially saw this and were quite alarmed. But we were able to demonstrate to them by using our verifiers that, in fact, this 128-bit path was dead code. It was never exercised in practice. And then the engineering team was able to remove it. And in previous audits, they hadn't seen this code because the engineering team thought this wasn't relevant, which shows sort of the reason why human judgment is so important to remove from this sort of process. And then with this path removed, our verifiers verified the code. And so now the code is fully compliant. Secondly, we also asked the developers what they thought about using the verifiers. And they told us that this saves their team, one of them told us that it saves their team 2 hours every 6 months, that is every time that they have to face an audit. And they also don't have to worry about failing an audit control. And 2 hours every 6 months may not sound like a lot, but it's worth noting that this is per team, per audit, per control. So this is basically just taking away an annoying task that the developers had to deal with every few months and making it nothing. And so that made them very happy. Finally, we ran another case study of 2 of our verifiers as part of AWS's security scanning infrastructure. So this was the key-linked and crypto algorithm verifiers, and we scanned everything that was security relevant at AWS, so not just the compliance relevant code. And this amounts to about 70 million lines of non-comment, non-blank Java. The results, the vast majority were verified, an absurdly large number of code packages. And then there were a few true positives and just 1 false positive in all of this code. A couple of things to note. First, of these 37,000 and so in the verified box, 99.94%, that is all but 23, required no human intervention. So we didn't use type inference here. We manually wrote type annotations for those 23 because that was not a particularly large workload. Second is that all of these true positives were validated by a security engineer, and none of them were in code that was relevant to compliance, which we checked with compliance. The security engineers drove the findings to completion. So these are no longer a problem. So this is all gone. So the last thing I want to show is a few lessons that we learned during this process. First, verification is a good fit for compliance. The 2 are naturally allies. This is because auditors really would like tools that are sound to eliminate the need for manual work. Right? And also that most of the controls that the auditors are enforcing manually are simple and local because they need to be enforced by a human who doesn't have in-depth knowledge of the system. That makes them amenable to verification. Secondly, verification is useful for stakeholders other than the programmers themselves. So in our case, it's compliance auditors, but there are other people who are interested in how the code behaves other than the people who wrote it, like managers or security reviewers. And we found that we're able to have impact in practice by focusing on this other set of stakeholders and actually deploying verification technology to their benefit. And lastly, we found that verification can actually save time for developers. This is a little counterintuitive, but that's because instead of adding another verification task to developers' already large workloads, we removed a task preparing for compliance audits and replaced it with the use of verification. And developers love that. That's all. The tools and data for at least the open source experiments are publicly available. See the paper for the link. That's it. I'm happy to take any questions that you have. Thank you for listening.